And so you said that forging can be used on a range of materials and different geometries. What do you think the most common thing that either you forge or like the world forges in general is?
Oh boy. There's so many things that are forged. I'm going to say probably the most common thing
Mhm.
are
Hey everyone, welcome to the It's a Material World podcast. I'm your host, Puneeth. I have my co-host with me, David. How's it going, David?
Pretty good. Yeah, well, actually, we're both putting the final preparations on about to go to a conference in Barcelona, Spain called Puzzle X. So we're both super excited. I guess because this is a learning podcast, one thing that's good to note is that to exchange foreign currencies, you have to go to the branches. And so today is the 11th, so it's Veterans Day. Unfortunately, banks are closed today.
Yeah.
So definitely recommend if you want to change currency in the US, do it plan a little bit earlier. So there's an extra tidbit on top of today's topic, which is what for me.
Yeah. Our topic is forging, which I'm not sure is related to foreign exchange, currency exchange. That is a good tidbit, and we'll both have to leverage airport currency exchanges for that. But yeah, that's super exciting. We're very, very excited to go to Barcelona and help out with being media partners for the Puzzle X conference. And we'll be able to help interview a bunch of those speakers there. So that'll be amazing, a great experience. But for the topic of today's episode, it is forging, touching on metallurgy and the applications of forging and even what does the future look like for this space. And I thought kind of my favorite part of the episode, one, Pat was super passionate about this topic, and that was evident throughout the entirety of the episode. And then two, the impact of computational modeling on improving forging processes and being able to save money by kind of gauging, oh, here's how it could perform, or here's what the properties could look like in the processing. So that was something that I thought was really cool, is just the effective computational modeling in so many different aspects of this industry. What about you?
Yeah, no, I think that the point about the modeling as well is that it could help with tooling. And so for people not so familiar with manufacturing, is that tooling is a huge upfront cost. And so you really don't want to get it wrong because it takes weeks to like manufacture a die and then to do it. And so I think that's another cool part about computational modeling. Other than that, he also touched on how new technologies such as like additive manufacturing or 3D printing, while won't usurp like forging as like the like marquee way to like do these large metal structures, it could be used in conjunction. And
Mhm.
so just continually improving upon and leveraging the best parts of each different like technology is like the future and how they plan on like tackling the next steps of technology to remain ahead of the curve.
Yeah, and based on that, like these are very large ingots that they're processing, right? He mentioned 116 inches in diameter, which is
Mhm.
crazy. And so I was wondering, what are some of those potential applications? And one thing that was very surprising to me is that there is a market for personal submarines, like not just for for like military use or whatever. So that was a very unique application there. Yeah, anything else that we want to get into before diving into the episode?
No, I was also very surprised that you could buy your own personal submarine. And so he did give a shout out. If you won the $2.1 billion Powerball, he said, feel free to contact him. He'll help you build a personal submarine. So
Yeah.
if any of our listeners out there want to go to him for your submarine.
I'm just wondering, like, who would want a personal submarine? I'm like billionaires, there's probably money for it, but like the
Mhm.
demand, that's crazy to me. But yeah, before we get into the episode, feel free to join our Discord community. The link will be in the description. And leave us a rating and review. It goes a long way to pushing this podcast out to other MSE enthusiasts. So without further ado, let's get into it.
Metamaterial Inc. is a developer of high-performance functional materials and nanocomposites. Meta delivers previously unachievable performance across a range of applications by inventing, designing, developing, and manufacturing sustainable, highly functional materials. Meta is a fast-growing company with a positive and committed work culture and a phenomenally talented workforce. Our employees are inspired to do exceptional and innovative work and are proud to contribute to the success of the company, and they are our greatest asset. Meta attracts people from all countries and cultures with over 35 spoken languages represented across all our teams. Meta believes that diversity drives creativity and innovation. With locations in Canada, the United States, the UK, and Greece, Meta is growing and is looking for new talented people to join the team. If you're passionate about doing your best work, making a difference, and having fun while doing it, apply to one of our open positions at metamaterial.com/careers. All right, hello everyone. For today's episode, we are thrilled to welcome Patrick Nowak, current plant metallurgist at Scot Forge. Since earning his bachelor's degree in metallurgical engineering at The Ohio State University, he has over 20 years of experience in metallurgy, mostly at Scot Forge, with a focus on forging, of course, and also heat treatment of high-performance stainless steels. Thank you for joining us today, Pat.
Thank you for having me. I'm very excited to be here.
Yeah. So to start, what exactly does Scot Forge do? And then since the focus of this episode is forging, can you just kind of outline the basics of this process?
Sure. So I'll start with what forging is and then talk briefly about the company, since the method of manufacture certainly predates the company. Forging is really a method of plastically deforming metal. There are other ways of doing that. You can do things like rolling or extruding. The difference between forging and those other methods is that with forging, you're moving metal in a small increment at a time. So say for rolling, you would take a large starting object and run it between two rolls, like two giant rolling pins, and you keep doing that till you get whatever the size is and shape that you're looking for. But with forging, you have either a hammer or a press or some other machine that has some kind of a stroking mechanism, and you put your metal between two surfaces that are going to come together. Sometimes those surfaces are really simple, flat surfaces. Sometimes they're very complex. But that's forging. Usually it's done at pretty high temperatures, and we would define that as the temperatures above which the metal will recrystallize when it's deformed. Sometimes forging is done at temperatures that are lower than that. And when that's happened, when we do that, we call that cold forging. And there are things that are made by both methods. Most metals can be forged. Actually, almost all of them can be forged. The ones that Scot Forge works with would be considered traditional structural and manufacturing metals. So all of the steels, the stainless steels, tool steels, titanium, aluminum, copper alloys, nickel-based materials, all of those are things that we work with. As a company, we've been around since 1893. The company was started in the Chicago area, Northern Illinois, and was initially very small, kind of just served the local market for forged products. And over time, it's grown, and now we are the largest supplier of what are referred to as open die forgings in the country. Open die meaning fairly simple shapes. We do some more complex shapes as well, but we're known mostly for the simple shaped things. In more recent years, we've gotten into both complex and very large complex shaped forgings. One of the unique things about Scot Forge is that we're a 100% employee-owned company. There are other employee-owned companies, but there's not a lot of them. And so we're very proud to be in that group. We've been employee-owned for about a little over 40 years. And 100% employee-owned since the late 1990s. And for those who aren't familiar with that business model, that's kind of a really interesting combination of being an entrepreneur and starting your own business, but at the same time having some of the benefits that come with being associated with a larger company, like paid vacation and retirement program and healthcare. And you get to have all of that kind of in one experience instead of having to sort of jump out and start your own business and be a sole proprietor. It works out very, very well.
Interesting. And I guess every employee has that incentive for the company to grow. So it's kind of just that added bonus there.
It does. Yeah, that's one of the big benefits. The model that we have here in the United States is one that's got some federal regulation around it. So that employee ownership model not only does what you just described, but it also dovetails into retirement And so
Mm.
as an employee owner, I am an owner. I know how much the value of my portion of the company is. That value is assessed every year by an independent auditing organization, but I can't access that money until I leave the company. And when I do leave the company, then that money would be treated in the same way as a 401k would be if you were some other company. So the government has rules about how you can take that money out and the age you have to be when that happens and things like that, because it's considered a form of retirement. But it still works out very, very well for those of us who are part of these kinds of organizations.
And so you said that forging can be used on a range of materials and different geometries. What do you think the most common thing that either you forge or like the world forges in general is?
Oh boy. There's so many things that are forged. I'm going to say probably the most common thing
Mhm.
are automotive components.
Mhm.
Mm.
So there's a lot of different parts on an automobile. For example, say for example, wheel hubs, where your wheel bolts on, and then that wheel hub is connected to other components of the vehicle and the steering mechanism and so forth. Those are often forged. That's probably one of the most common things. Probably many others that I'm not thinking about.
Mhm.
Things that we make um,
Mhm.
don't ever end up on automobiles.
Okay.
We make much larger components than that. So the things that we're producing are going into very large pieces of equipment. So we make things that people would recognize, for example, like axle components, but the
Mm.
axles go on huge mining trucks.
Mhm.
So yes, it's an axle. Yes, it has a flange where a wheel bolts, but that wheel might be 12 feet in diameter, and the truck may be able to carry 400 tons of dirt and rocks and things like that. So those are the kinds of things that we're making. We make a lot of things for a lot of different industries. We are particularly proud of the work we've done for the U.S. Navy on submarines. A lot of very large, complex structural components that go into submarines that are made by forging. But we've also made components for personal submarines. So
Oh.
if you're somebody that won the giant lottery that just happened earlier this week and you want to buy your own submarine, there are companies that do that, and we've made parts for those submarines. We
That is a
also,
market that I would never have imagined.
right?
Personal submarines.
Well, it's not a big market, but it's a market. There's been two different projects that I've been involved on for
Wow.
doing components for personal
Uh-huh.
subs. One of the other things that we talk about a lot, because it's something that a lot of people are familiar with, are the two Mars rovers that are rolling around
Mhm.
up on Mars.
Oh,
We made
Mhm.
nice.
the wheels for both of those.
Oh, wow.
Those
That's so
are
cool.
those are aluminum forgings, but yeah, so those are ones that a lot of people have heard about. So we mentioned those kinds of things, but there's so many different uses for forged components,
Mhm.
and most of them are things, at least the stuff that we make, are things that the average person is probably not going to encounter unless you happen to work in
Mhm.
an industry that uses those components.
Mhm.
You're not going to realize that's out there.
Gotcha.
But for example, electricity relies on forgings because you have to have generators. Those generators have to have great big shafts. Those shafts are forged. Um,
So a lot of subtle uses. So I guess I was just wondering, Pat, then, so you mentioned kind of some of the differences in the methods, like simple surfaces versus complex geometries. Can you give some examples of some of the applications for like simple surfaces versus some of those complex geometries?
Sure. So a simple shape might just be a long cylindrical form with varying diameters along its length. Okay. And that might be what we produce. And then we send that off to our customer, and then they may machine, for example, say gear teeth into a portion of that component, and maybe put some splines on the end so that it can go into a drive mechanism or something like that. But for what we're making, it's a very simple shape. A more complex shape would be like one of those axle components that I mentioned, which they have a flange on one side. That's the biggest ones. Those flanges are roughly 5 feet in diameter. The whole component may be 7 or 8 feet long, but it's formed in such a manner so that it's hollow, and it's got a flange on one side, a much smaller diameter on the other side, and we use specialty tooling to create that shape and minimize the amount of steel that we need to use to make the shape. And so that keeps the cost of the raw material down, and it keeps the cost of later operations down. If you make it hollow, then you don't have to machine that out, so there's less machining to be done.
So you, like I said in the intro, you have like 20 years of experience and you've given us all these great things that your company has made. What do you think your favorite thing that you've ever made is? And then any like personal anecdotes about these really cool projects that you've been able to work on over 20 years?
This is hard because I have my own blacksmith shop at home. So I forge
Oh,
not only
Oh, wow.
professionally where I get to use my engineering degree, but just outside the house here, I have a pretty substantial blacksmith shop and I make all kinds of things there too. So I'm using forging all around. But let's see, a thing that I maybe most, without giving a specific, there's one specific component, but it's got a military application, so I don't want to give too much detail about it.
sure.
But I will say that it's made from a duplex stainless steel, and it was a very large cross section. So figuring out how to successfully produce that part, it was a very challenging part metallurgically to produce, both
Mhm.
from a forging perspective and also from a heat treat and mechanical properties perspective. And when we were successful, it comes with an enormous amount of satisfaction. So I would say that one's one of my more recent ones. But anytime you have a job that's you're struggling to overcome some problem, and then you finally get that problem solved, and you're able to be successful and provide what the customer's looking for, there's a lot of
Mhm.
satisfaction that comes with that.
Got it. So what kind of metallurgical principles do you consider when you're trying to solve these like processing related issues?
No, there's a bunch of them. It depends exactly on which which kind of problems you're dealing with. When you're dealing with, for example, the duplex stainless steels, those are steels that exist both as ferrite and austenite at the same time. Most of the time, we think about steels as either being ferrite or austenite or martensite, depending on what kind of heat treatment you've done. But at normal forging temperatures, they're typically 100% austenite.
Mhm.
With duplex stainlesses, that's not true. You have both ferrite and austenite present at the same temperature, and those two structures have different yield strengths. So when
Mhm.
you're trying to deform them, one is deforming more easily than the other. So at the interface between the two structures, you end up with a shearing action and they want to tear apart.
Mhm.
So you have to then control how you do your forging so that that doesn't happen. They don't have very good thermal conductivity. So when you go through, well, let me back up just a minute. Those, because of the composition of those materials, when they're
Mhm.
cooled slowly, they will form a whole bunch of intermetallic phases that are
Mhm.
very embrittling and also kill your corrosion resistance. So you have to use rapid cooling to solution any of them, but the thermal conductivity isn't of the material isn't very good. So you can end up with high stresses in the part. And so if those aren't managed, then you'll crack the part. So
Mhm.
there's a bunch of different things that are all going on at the same time. If I was going to switch out away from duplexes and talk about more of a conventional, what we would call a low alloy steel, controlling grain size in some of them is difficult if you don't have sort of typical grain pinning materials like aluminum nitrides are the most common in the steel industry, but some steel grades have restrictions on aluminum, so you have to use other grain pinning elements,
Mhm.
which may dissolve at different temperatures, and you lose your grain pinning effect at a different temperature than you do with the aluminum compounds. Another challenge we deal with is controlling grain size in materials which do not undergo phase transformations. And so this is true for both austenitic stainless grades and your nickel and copper alloys. And so
Mhm.
now your control of grain size is really a function of controlling strain and strain rate and temperature. Basically, you're dealing with dislocation. So if you've ever studied dislocations and what happens inside of a crystal during plastic deformation, you have to control the quantity dislocations and the temperature at which they're developed, because if you get too many at the wrong temperature, you'll trigger a recrystallization event. But if that happens at the wrong time in manufacturing, you end up with the
Mhm.
wrong grain size. So I've got all kinds of principles that just
Mhm.
depends on the moment as to which ones I'm thinking about.
Yeah.
Mhm. So Praneeth and I both took a alloys class, so we understand about like these principles such as the grain pinning and grain size, growth, etc. But I feel like that's a very theoretical approach. For you, when you get a new order for a customer, what does the analysis from we need this yield strength to figuring out exactly the heat treatment or the force you apply or all the other different parameters look like to get to the end product which they want?
Sure. So it depends on the grade and the properties that they're looking for.
Mhm.
If we're dealing with say a carbon or low alloy steel, the salesperson takes the order. Then we've got someone who will construct the individual work instructions to make that part, and then it goes out to the shop floor. If there's going to be a requirement for mechanical properties, so like a yield strength requirement or something of that sort, then it's going to have to go through some kind of a heat treatment operation. If there's a question as to our ability to hit those properties, then a metallurgist will be involved to review that in advance and determine if we can hit the properties. Sometimes we will come back to a customer and say, what you're asking for and the grade of material you've asked us to use are not compatible, and we need to offer an alternate grade. Sometimes we have to look at, narrowing down the heat treatment parameters. So we may have to have a very tight control over tempering temperature, for example. We may have to have very tight controls over the quenching process. This is especially true if you have a more complex geometry and you're concerned about having a crack in the part. Then instead of just heating it up and cooling it off down to the quench bath temperature, you may have to stop the quench at a higher temperature. So basically determine a length of time to have the part in the quench bath, and pull it out of the quench bath and allow the remaining cooling to happen at a slower cooling rate, or even put it right back into a furnace at a lower temperature. To get to that understanding, then we may have to use some computer modeling. And we've got computer modeling tools that'll help us to assess stresses over time during quenching operations. And they're actually extremely helpful with that type of work.
And I know we'll get into computer modeling later and its effect on the forging industry. But first, I wanted to really focus on metallurgy. And you've outlined the importance of it in the forging industry. But for MSc students who may have an interest in alloys, metals, etc., even if they don't end up in the forging industry, can you kind of outline the importance of studying this discipline within the field of material science?
Sure, absolutely. So steel, just the metal steel, is the second most widely used material on Earth. The first is concrete. So now steel, we say steel, and if you're not in the discipline already, you might think of steel as just a single kind of metal like gold or silver or steel. Those of us that are already in that field understand that it's more complex than that. And for those listeners who don't have much background in that, I would like to use a food analogy. I happen to really like ice cream, so I'm going to use ice cream. The world of steel is very much like going to an ice cream shop where they have a whole bunch of flavors of ice cream in the case, and you can pick whatever you want. And then they've got another case or a display that's filled with different toppings, and you can put anything you want on there. And of course, they have different serving sizes. So if you think about the math to determine the number of options you have, if you go to a store like this, if you've got 20 flavors of ice cream to choose from, assume you have 20 topping options, and maybe there's 4 different sizes. How many different combinations of choices as a customer do you have? I tried to figure that out one time and I got stumped, but it's 10 with a couple of exponents above it. It's a lot, right?
Yeah.
Now, in the world of steel, we have composition, size, cooling rate, various heat treatments. And so you can see, and composition, you have a lot of different elements that you can pick from in all different proportions. So you can see how the number of choices we have as people working with metals, working with steels there's a lot. I don't have the exact number, but it's a big number. To get the most out of those options so that we can have the best performance in whatever those criteria may be. And I'll use an example that's perhaps current, which is trying to become very efficient in transportation, right? We have for a long time had a desire to have good fuel economy and internal combustion engines. Now there's a shift towards electric driven vehicles. But in both cases, you're trying to get the best efficiency of transportation. So that part of that is having the lightest vehicle you can, but at the same time, you need to protect the occupants. So you have to have a certain combination of lightness and strength. That requires somebody with a good knowledge of metallurgical principles, both understanding composition and process to figure out how to get the maximum out of those materials. Steels are ones that we've used traditionally for that. But as we make advancements in other alloys and alloy development, we find that it's possible to shift to aluminum. So some listeners will be familiar with one of the recent truck companies coming out with a kind of an all aluminum bodied pickup truck. And there's other things that are done. And of course, when you're in a particular alloy industry, the steel makers, for example, recognize that aluminum is lighter than steel. So what are they, if they want to stay competitive and stay in business in that market, they have to figure out how to produce a product that's going to meet this new need, because their competition is a different metal, an alternate metal. So there's always a desire to get better and better, to become more efficient. And that's just one example. There's many, many that we could look at.
And so, yeah, that building upon and continuously improving, not only from the metallurgical side, but also from the forging side. And so, like you said, forging predates your company by like maybe hundreds of years. How
Thousands of
do thousands of years? Yeah. So
thousands
it's
of years. Yeah, for
so
out a
so
long time.
so it's obviously not the same since thousands of years ago. But how does the industry incorporate these new technologies to not only improve from the metallurgical side, but improve from the like actual forging ability that you have?
Sure. So one way is to create equipment that can produce more power.
Mm-hmm.
So at Scot Forge, when I started there, it's been about 19 and a half years ago now, we had, I think our biggest forging press in terms of the power that it could deliver was about 3,000 tons. Today we have a press that can deliver a little over 16,000 tons. That power, and of course it's physically a larger press with a bigger working window, allows us to do things we couldn't do before.
Mm-hmm.
We've partnered with one of our primary steel suppliers, and in the time that I've been working with them, they've gone from being able to create an ingot that weighs about 50 tons to ingots that weigh 220 tons. That's a big piece of steel.
Yeah.
That and that's not the biggest that's available in the country, but it's close. And so we, as an industry, we are increasingly adding to our manufacturing capabilities to meet new needs. Those great big things are used to make components, some of them for submarine components, some of them for power generation applications, where, for example, if you're making components to go into a nuclear reactor, you want to minimize the amount of welding that has to be done to create the housings for those things. So if you can make bigger and bigger components, there's fewer and fewer welds that have to be used.
Mm-hmm.
So that's one driving force. That massive power allows you to make more intricate shapes. If so, when a customer is asking for things that have a lot more contour and complexity, we have the ability to do that. So I would say one is just keeping the power, keeping the equipment on the cutting edge of what's available.
Mm-hmm.
The speed of how fast the equipment can work, so that you're as efficient with your manufacturing time.
Mm-hmm.
Supporting assets, so not just forging, but then forging coupled with heat treatment equipment, coupled with machining equipment, so that you can provide everything that the customer needs. That's on the equipment side. One of the things that we should talk about is having the right people involved. Forging is a very much a skilled trade, and it's one that you can't really go learn outside of a forging company unless you're going to learn hand forging in a blacksmithing kind of setting. So you have to target people who have a real willingness to learn that trade. From the metallurgy side, we need people who can not only understand sort of I would say the traditional, the already established metallurgical principles, but because our customers are asking us to do things that haven't been done before, we need people who can figure those problems out, whether that's through some on-site research, relying on knowledge they've acquired in the past. But we're constantly being asked to solve problems that stretch us. So you need people who are willing to step up to that challenge.
Awesome. And so then I know you touched on like the computer modeling, computational modeling, and I'm sure that also helps in terms of the continuous improvement of your processes. Can you get into that and
Sure.
what can maybe our audience do to better equip themselves, and get that skill set from the computational perspective?
Yeah. So on the modeling side, right now there's two areas where we use a lot of modeling. The first is in understanding metal deformation in complex tools. When a customer asks for something that's not a very simple shape, it's more complex shape, then we can create tooling to generate that. But you want to make sure that you can use the models to design the tools virtually, and ensure that they're going to be functional and give you the results you want before you actually invest in manufacturing the tool. So that's a big, that's been something we've really added in the last, say, 15 years. And that's become a very important part of what we're providing for our customers. The other one is one I mentioned earlier, which is the modeling of heat treatment, looking at stresses during quenching. And one that we are starting to explore more is solidification modeling. Now, we're not a steel maker or a maker of anything. We don't produce any of our own raw materials. We purchase all that from various vendors. But some of the things we make are really, really large. So I mentioned these great big ingots. So an ingot like that may be, 116 inches in diameter. And the solidification time on something that large is very long. What happens when you take a big container of liquid metal and allow it to solidify like that? It doesn't all solidify instantly. It solidifies over an extended period of time. And so you end up with a separation of composition. Even though the metal may have been homogeneous in the liquid state, as it solidifies, there becomes composition gradients. And we're starting to think about now, how can we better understand those composition gradients? Because once the metal's solidified, there's not much we can do as a forging company to change that distribution of composition. So if we have a better understanding of how it exists, then we can do a better job of utilizing that material to, again, meet our customers' needs. So that's just something we're just beginning to look at. But anything like that is going to be of value to a student or a young engineer being able to work with those kinds of tools.
Does that composition gradient lead to like anisotropy or a change in properties, like from one side of the material to the other?
It can, sure, absolutely. It's not usually so much from one side to the other, but from, say, a near surface region to an interior region.
Out. Okay,
yeah,
makes sense.
What you end up with is that the areas which solidify last tend to have the highest alloy content. They also tend to have the highest concentration of non-metallic inclusions. In some circumstances, that variation in composition changes the transformation temperatures to such a degree that when you go through normal heat treatment practices, the interior region, say on quenching, for example, may still have some retained austenite. And after tempering and then cooling after the temper itself doesn't force the retained austenite to transform to martensite or bainite or whatever the structure is going to be. But after you're done with the temper and the part presumably is now allowed to cool, say, all the way to room temperature at the core, you get a transformation. Say, let's just assume martensite. So now you have untempered martensite in the center of the part, which is quite brittle. That could lead to a crack. I've seen this happen before. So these are situations where if we understood that better, we'd be able to alter our heat treat practices to ensure that after quenching, we cooled to a low enough temperature to actually get the transformation we need before we start the temper. Or perhaps figure out some way to remove, and if the forging was eventually going to have, say, a bore in it, you might be able to selectively utilize that material and say, well, this metal we should use for hollow forgings, and maybe this piece over here, which has got a different segregation pattern in it, we can use for solid forgings. That would be a way of using that kind of information.
And so computational modeling is extremely useful for like what happens from the beginning to end. So most of what we know today, I'm sure it's extremely hard for like this 116-inch diameter ingot is to do like in situ experiments where you can see what's happening during the process. So now that you're building these capabilities to understand what's happening, have there been any things that you didn't know exactly how to explain, but like surprised you when you're finally able to model it and see what was happening to understand, to explain the phenomena between the beginning and end?
So far, we're at kind of the beginning of the modeling stage. But what's quite interesting to me, I have a kind of a passion for history in addition to the metalworking side, and I've been spending a lot of time reading older metallurgical books and papers. And so something like this segregation description that we're talking about here, knowing that it's happening isn't new. When you go back 100 years ago when large ingots were sort of they were kind of a new thing in the market. People cut them in half and did chemical assessments, and so you can find in books from the period descriptions and where they actually would map out the composition of an ingot with whatever precision they had with their measuring instruments at the time, which of course are different than today. So at the moment we're taking and using modeling to, I think from my perspective, it would be, I would want the models to demonstrate that they're as good as what people have already done with physical testing in the past. And once the models are that good, then we can work on making them better.
So that's kind of one aspect which you are already planning to build out is the modeling capabilities. What do you think the rest of the future of forging looks like? What other areas are there room for improvement, especially like within the next 5 years, such as like metal 3D printing or additive manufacturing?
So that's a really good question because those newer technologies are certainly generating a lot of excitement in the engineering and manufacturing world. Sometimes, it might look at those technologies as competing technologies to forging, right? For certain applications, that's probably true. There's probably some things where those technologies will be able to meet a need better than the forging can. But I think that the majority of forgings are still going to be, I don't think that they're going to be strong competitors. I think that those technologies are going to be complementary technologies, largely because of, well, there's two reasons. One, when you're dealing with additive manufacturing technologies, and there's a bunch of different ways that you can do that, you end up quite often with materials which are not 100% dense. And that means they've got little internal voids and so forth in them. And those will change the mechanical properties. So if you have an additively manufactured component and a forged component of the same alloy with the same hardness, they're not going to have the same properties. Now, you might be able to get them to approach the same properties if you subject that additively manufactured part to, say, for example, hot isostatic pressing or some additional secondary processing. But there's a cost to doing that. And additively manufactured parts right now, the raw material for those metal powders in particular, are extremely expensive. So at the moment, they're not a financially viable alternative to most forged components, but they're a great fit for certain one-off applications. An example that comes to mind would be like in the world of medical devices and medical implants, where you're trying to create a custom component for an individual patient, where it's very much a unique item. Provided you can get the mechanical and corrosion properties you need, an additively manufactured part might be an excellent fit for something like that, where if you were going to make the same component by forging, you may be able to do it, but you'd make a slightly more generic component, and then someone would have to manually tune that component to the patient. So there's definitely a spot for that. The other area, which is getting a little bit of thought right now, and it's just sort of I would say at the beginnings of being investigated, is the idea of combining technologies, so that you would start with maybe an additively manufactured component and then do some forging on that component in a targeted way to enhance properties in a local area. That's just like, people are just starting to talk about that. I'm not sure that anyone's actually tried it yet, but it's definitely things I've been hearing about at the universities when I visit, things like that. So I definitely see that as a future area for exploration.
And so I know with additive manufacturing, like repeatability in properties and performance can be a challenge. I'm just wondering, from the forging perspective, how do you ensure that each product has a high quality and that you can, have the repeatable performance from that side of things?
Yeah, so that's a great question. I'm going to say that, and this is probably true even for other manufacturing technologies, not just forgings, not just additively manufactured components, but it's a rare circumstance to find something which is truly uniform and exactly the same from one item to the very next item. There's always some amount of tolerance, some range in the manufacture of anything. The actual limit on that spread is dictated by the application. So some things, like, let's say, rotating jet engine components are going to have a really narrow tolerance for that. There's still going to be a little bit because you just can't make everything perfectly, absolutely identical, but that's going to be pretty narrow. Other applications can tolerate a lot wider range, but within the acceptable tolerance for the application, the way you do that is you do things like you put tolerances on the chemistry of the raw material you're starting with. You put tolerances on some of the manufacturing, for example, maybe some of the forging parameters may have certain limits. Certainly with heat treatment, you have defined temperature ranges. And then within the furnaces, you have furnaces that are subjected to things called surveys, so that you know the furnace itself is going to hold its target temperature within a certain plus or minus range that's allowed by specifications. Specifications, whether they're generated by a customer or by an industry organization, for example, ASTM would be one. Specifications do an awful lot to help ensure that we have the appropriate levels of uniformity in the things that are made.
Awesome. Well, yeah, I think one thing that I wanted to just touch on, since you mentioned that outside of your professional work, you do bladesmithing or blacksmithing. Is that
And
right?
bladesmithing. Yeah,
And
I got
bladesmithing.
started actually making knives, so bladesmithing is
Okay.
part of that. Yeah. Mhm.
Accidentally correct. So I was just wondering, for students who might be interested in doing some of that, do you have any advice for them in terms of how to get started?
I do, yes. So from my own experience, I was making blades by the stock removal method. I think by the time I was in junior high school, and I was really interested in forging, but I did not get into forging until I was in college. But I had been given some resources by a local blacksmith, and I didn't really take advantage of those, mostly because I was a little bit nervous to reach out to people I didn't know, which might not be that unusual when you're in high school or even in college. In the end, I met some great people, and I've spent probably 25 years in the blacksmithing community, and it's a great community. So my advice would be to a young person, if you're really interested, just start. Even if you don't know exactly what to do or who to go to, take some step to get started. Even if that's just to grab a hammer and a rock and use that as an anvil, you can start, right? The people in the blacksmithing community, and the community has grown a lot in the 25 years that I've been a part of it. Everyone is really, really willing to help. So even if you don't have a personal connection, you can jump on a whole bunch of different online resources where there's various groups and so forth, and you can find blacksmiths in your area. It's rare today to not have a blacksmith in your community, because the hobby has grown, and most people are willing to help others get started. If you really don't have anybody in the area, you can still get started just with really, really simple tools. I would say if you're interested in blacksmithing, don't feel like you have to have all of the traditional looking tools. So I wasn't kidding when I said a rock will work. Like, people have used rocks as anvils before. They've used large meteorites as anvils before. One time I had an opportunity, a friend of mine had a tombstone which was never put into service. It had been, I don't know, whatever image they were going to put on it, there was a mistake, a flaw, something. So anyway, it did not end up in the graveyard. It ended up in his workshop, but it was really flat because it was a tombstone, and we forged on that, and it actually worked really, really well. This seems a little counterintuitive, but from the engineering perspective, the thermal conductivity of a piece of granite is much less than that of a piece of steel. So it kept the workpiece hotter longer. So it actually had some advantage there. Yeah, yeah. So I would say just take the initiative to get started, even if your efforts are crude and minimal and so on. Just start. And when you have an opportunity to connect with somebody with more experience, take it. Even if you don't know them, introduce yourself and jump on it. I think that would be my advice for young people that are interested in starting, or anybody really. I mean, whether young or old, anybody can do this. I would say also not to be intimidated by it. You're playing with hot metal. There's a certain level of intimidation and safety concern about that. And those are real concerns, but there's very easy ways to deal with that with appropriate PPE and so forth. The other thing is that if somebody wants to try doing a little bit of forge work, you don't have to do hot work. You can do even really simple forge work with things like heavy gauge copper wire that can be worked at room temperature, and you do small jewelry items and things like that. So there's a lot of avenues for a person to get into doing some hand metal work. And the other thing is it can be very inexpensive to start. You can start with a very low investment.
Awesome. Awesome. Yeah. And I know that TMS has like a bladesmithing competition as well, right, for
Yes, they do.
university teams. So that might be something that students can explore in their own universities,
Yeah.
right?
So depending on the school that you're at,
Mhm.
TMS is certainly one that a lot of people will know. Many schools now have blacksmithing clubs because folks have demonstrated interest in it. So they find a academic advisor for the club and some resources. So that's pretty common. That's probably the easiest way for a college student is to look and see if there's a blacksmithing club on their campus. Many of them have them now. Some community colleges now offer blacksmithing classes, and a lot of local blacksmiths will offer one-on-one training. There's a fee for that, just like you would for any other educational experience. But that can be a great way to get started, because then if you have the ability to do something like that, your learning curve will be shortened substantially as compared to just trying to learn it all on your own.
Awesome. Well, thank you so much, Pat, for joining us today. I learned a lot about forging that I never would have imagined. So it was truly a great discussion.
Well, it was my pleasure. I'm really glad you invited me.
Awesome.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.